Rust Atomics and Locks. This is a fantastic book. If anyone doesn't have it, you can get it online. You can buy it from most retailers. There's also, I don't know, Alex, if you want to drop in the chat the link to Mara Bos's website where there's the content. So if you want to follow along, this is going to be going through the book pretty closely because it's pretty great. The book brings together the pieces which underpin the Rust concurrency primitives that we use and eventually get into some of the trade-offs and the reasons behind the designs. Chapter 1 is all we're going to have time to cover today, I think, which is the basics of Rust concurrency. And then Anup's going to take chapter 2, atomics, later, future session. And we're going to be looking for new people to take on future chapters. So if you might be willing to go through a chapter in one of these meetups and talk about, things you notice, things that you didn't understand before, but you understand now, or just generally just describe the content, then yeah, please reach out because we're always looking for new speakers. The chapters go through onto like building your own arc, understanding the processor, operating system primitives, building our own locks, and then like how to take it further. This is the this website. So the top link is the atomics book where you can buy it from O'Reilly. You can also get it places like Amazon, and the website marabos.nl/atomics has the content if you're looking for it. So chapter 1, this covers threads in Rust, shared ownership and reference counting, interior mutability, thread safety and the traits sync and send, locking through Mutexes and read-write locks, that W should be lowercase, and waiting using parking and conditional variables. So yeah, always kind of be a whistle-stop tour of all the essentials. Feel free to like shout out if there's anything you think I've gotten wrong or haven't described properly, or just want to enter into discussion a bit, but there'll be time for discussion at the end as well. So every thread starts with one thread, the main thread, and we can spawn more threads with std thread spawn. Every thread has a unique thread ID, and if the main thread finishes before the spawned thread, then the program still terminates, so you won't necessarily see the output from those spawned threads. And just to be very clear, we're talking about operating system threads, not things like green threads, Go routines, MN threads, lightweight threads for async programming. This is talking about the operating system threads. So this is, one of the simplest examples. You have some function and you use thread spawn to spawn multiple instances running on different threads. In this case, it's saying hello from another thread and then printing its thread ID. You can get different ordering from these results. I ran it quite a few times. I didn't get any different ordering, unfortunately. But in theory, in this case, because we're spawning those threads, but then they might not complete in time, you could end up with just hello from the main thread, maybe one message of hello from another thread, but then never get the remaining set of messages. So that's why you have this idea of joining threads, which means that the thread you're on is going to block until that thread that you're joining completes. And you do that using the join handle that's returned when you spawn the thread. Join returns an error, and that's because the thread in theory could have had a panic. And if it panicked, you might want to terminate the main thread. You might want to do some special behavior. So that's why it returns an error, so you can see what happened and propagate those errors. So this is an example there. If you spawn a thread that in this case it's just going to do a panic, so it's going to essentially throw an exception. And then if we join on that thread, we can say we expect this to never throw an exception. And then that will immediately propagate that exception to the main thread and cause the program to shut down. And we can see it panicked at, oops, panicking again. And that's the inner exception message. And this is the outer exception message. In those cases, we were passing functions in, but you can just as easily pass closures. We have to use move in cases where we would be capturing by reference, and that's because otherwise we don't know if the reference would live long enough. So what move does here is it ensures that the vector is captured by value rather than by reference and transfers the ownership into the thread. So numbers can no longer be used in the threads that's spawning this inner thread. It can only be used inside that spawn thread. And essentially that's to do with the lifetimes. So thread spawn has a static lifetime bound on the arguments, which means any references that you're using in that closure need to have a static lifetime. And that's because the thread might live as long as the program. You don't know when it's going to get joined on or if it's going to terminate. There is, however, now scope threads. I can't remember what version these were introduced in. I feel like it might have only been last year. But what these do is allow you to specify a scope, and then from within that scope, you can spawn threads that can capture references, provided they live as long as the scope itself. So in this case, numbers we know lives longer than the scope. Therefore, we can use a reference to numbers inside of those spawn threads. So we don't need to use the move keyword anymore. We can just capture numbers by reference. The usual reference rules apply. So you can only have one mutable reference with no immutable references or many immutable references. That's the same as usual when you're doing that capturing there. If you're capturing by mutable reference, then you can only do that on one thread. It's worth saying that thread spawn is just a shorthand for thread builder new spawn unwrap. If you use thread builder directly, you can give the thread a name, and you can also give it a stack size. And this is something that came up in the Discord chat. People were talking about default stack sizes, and the threads you spawn also have stack sizes, but you can change those stack sizes to increase them if for some reason you need a larger stack. And the unwrap inside there, inside the std thread builder new spawn unwrap is because spawning a thread can fail. So your operating system could say, sorry, I can't spawn that thread. I'm out of memory. I've hit some resource limit. And in that case, there's going to be an exception. So just to summarize the threads bit there, you can spawn threads with a function or a closure. You join threads to make sure they complete. Use the move keyword to take ownership of data. And scope threads allow parent threads non-static data to be referenced from inside the thread. Whistle stop tour. Cool. So now we're on to shared ownership and reference counting. Static data has its lifetime tied to the length of the program, and by convention, their names are screaming snake case, and they're typically data known at compile time, but not necessarily. Because, and I've never used this before, I was really interested to read about it. You can use forget, and you can use box leak to make data static. So in the other example, when we had a non-scope thread, we had to move the data in. But if we didn't want to move the data in, and we didn't have scope threads, we can actually still make it work. So in this case, we would get an error on the lifetime of our numbers data. But if instead we leak the numbers data, so what we say is, don't drop this data, like just let the memory keep existing. That data then becomes static, and it's going to live from the moment that you leaked it to the end of the program. And I hadn't really considered the fact that static data isn't data that exists from the start of your program, it's just data that lives till the end. So now if you've leaked this numbers, I mean, you have no way of cleaning it up. It's essentially a memory leak, but kind of so static data normally. So if it's just one big object that you know you're going to be referencing, then yeah, you can use box leak, and that way you can reference it from inside this spawn thread here without using a scope thread. And it's worth saying that forget is considered safe. So forget is similar to box leak. And that's because you could implement it safely, therefore you can't make it. I think originally they had it as unsafe based on what I'm reading in the book and online, and then they made it safe because you could implement it with other safe code, therefore it was kind of inconsistent otherwise. So you can, if you want, you can leak memory. It's nice to have options. So in this case, if you use this forget method, which doesn't use any unsafe code, and then your drop method will never get called, even though drop is implemented on don't drop me, because you've essentially made it static. In this case, there's no references hanging around to it, unlike box leak, which gives you back a reference. This one doesn't. But you wouldn't normally do that. Those are unusual things. What you tend to have is reference counted types. So these allow you to have multiple owners of the same reference, and the last one holding a reference, when that goes out of scope, it will do the actual drop of the data. Use RC for reference counted for single threaded use cases, and it contains a reference count showing you how many active references there are. There's also ARC, which is an atomic reference counted. So for people coming from a C++ background, shared pointers are all atomically reference counted. As someone correct me if there might be another type that's not, but they're generally atomically reference counted. Whereas in Rust, there's two distinct types because you don't necessarily want to take the hit. An atomic reference counter is slightly more expensive than a non-atomic one. So for that reason, in Rust, there's two separate types. And the atomic reference counted one is the one you would use if you need to use it across multiple threads. And that's because as you increment the reference count, you need to know that no other threads are incrementing it at the same time, or if they are incrementing at the same time, that you'll still end up with the correct number at the end. You won't have one thread saying, oh, the reference count is 2, I'm going to make it 3, and another thread saying, oh, the reference count is 2, I'm going to make it 3. They both make it 3, but they both think that they've incremented the reference counter when in fact it actually hasn't incremented by 2 like it was supposed to. You create the multiple owners by cloning the reference counter type or the atomically reference counter type. And then you move that new atomic reference into the thread's closure. So this clone is cheap. It's not like cloning a string. It's not doing an allocation. It's incrementing a reference count. So in the atomic case, it's the cost of doing a single atomic operation. This was a quite nice little tidbit that I hadn't thought about. Like naming arcs is slightly awkward, and when you have to like clone it, and then you're like, well, what do I call the clone? What do I call the new one? I hadn't really considered the fact that it's quite nice to just, if you just put a scope in, then you can give it the same name and shadow the outer one. This was, yeah, a nice little tidbit in the book of like, by the way, you might want to do this. Not really exactly relevant to the core content, but it's yeah, a nice way of doing it. So I thought I would share that. So just to clarify that again, so you have your atomically reference counted type here, but rather than saying let B equal a.clone, you instead create a scope inside your spawn, and then you can do let A equal a.clone without losing this A, because this A is only shadowed for the extent of this scope. So this is still the original A, but yeah, quite nice syntax. And onto borrowing. So immutable borrowing, you do the reference, mutable borrowing, ref mute, and as we've kind of discussed a few times at various other meetups and earlier in this talk as well, you can only ever have one mutable reference active at any one time, and you can't simultaneously have an immutable reference with a mutable reference. You can only have many immutable references or just one mutable reference. And there's benefits to that that you don't get in languages like C++, which is things like the compiler can assume that two references are not aliases to the same data if one of them is mutable. So what that means is if you have a function which takes two i32s, A and B, in C++, like there are like annotations you can add in certain compilers to say, I promise that these are not aliases to each other. But generally, people don't necessarily do that all the time. So the compiler can't assume that A and B don't impact each other. So if you change B, that could change A if it's possible for those two references to be aliases to each other. But in Rust, because of the borrow checker and the rules that we have in place, we know that B is never going to be a reference to the same thing as A, which means A before and A after are going to be the same. And therefore, the compiler can just make decisions based on that, can remove blocks of code entirely, which is, yeah, convenient for making your code more efficient. And when you use unsafe code, you're still subscribing to those rules of the borrow checker. You're just saying that you're going to ensure them. You're not saying that you shouldn't be passing around two references where one is mutable and one is immutable and they're the same thing, because that does still violate the assumptions that the compiler is allowed to make. And that can cause really weird behavior, which is described really well in the book. And again, this isn't something I'd thought about before, and it's really interesting. if you had some code, like for example, using get unchecked. So with get unchecked, you are not doing a bounds check. And if you put in an index that was out of range, it's undefined behavior, you're going to be reading into some random memory. It's generally a bad thing. But the compiler can make an assumption that you are doing it correctly because you have said, that you've said that this won't be out of range, because if you weren't saying that, you'd be wild. And therefore, it can also make that carry on that assumption to earlier in the code. So in this case, it knows that this array A has 3 values in it. If it also knows that the index is going to be within the bounds of this array, then it knows that it's going to be less than or equal to 2. Now, since the index hasn't changed between here and down here, that means that this branch should only ever have the case of 2 in it. It should never occur with the index equal to 3, because if it did, you'd have been violating rules later, and it's allowed to assume that you didn't do that. And therefore, the compiler could potentially optimize Z. If this is the only place that Z is used and it only takes a 2, then it can say, okay, well, I'm not even going to bother compiling code that would handle different indexes, because it's only going to be 2 ever. And so it's completely undefined behavior if you violate these rules. So yeah, more fun facts about unsafe code and compiler assumptions. Okay, so far we've been dealing with kind of your typical reference types, where you think about like an immutable reference and immutable reference. But in Rust, there is this idea of interior mutability. We've discussed this in previous talks before, and these allow mutation through immutable references. So even atomically reference counter types and reference counter types are technically mutating, which is, again, a nice little tidbit from the book. Because if you think about it in the sense of the reference count inside the data needs to update, even if it's an immutable reference, well, then, yeah, I mean, it's technically got interior mutability. And in types where the data is changing, even when you have an immutable reference, it's not necessarily useful to still call it an immutable reference, because the data inside can change. So it's a bit confusing. So instead, you might want to say that ref T is a shared reference, and then ref mutable T is an exclusive reference, because these reference types still obey all those reference rules that we talked about a second ago, where you can only have one mutable reference at any one time, and you can have many immutable references. So you can think of ref T as a shared reference and ref mutable T as an exclusive reference, if in the case where T is an interior mutable type. Some examples of the types of interior mutable types. There's cell, which is quite a nice simple one. It has a get method and it has a set method for modifying, and that's it. It's single thread only. It's pretty basic, but very useful. Then there's ref cell, which also allows you to borrow the content. So with cell, you have to actually get the data out, modify it yourself, and then set it back in. You can't modify it in place. But with ref cell, you can. And the reason you can do it with ref cell is that it keeps track of how many borrows have been done, and it won't let you get a mutable borrow if there are any other mutable borrows, or even if there are any other borrows. And those reference rules are checked at runtime, and it panics if you can't get the borrow, because it would be undefined behavior to try and write to that data while someone else is looking at it, or while someone else is potentially modifying it as well. And again, that's single threaded only. There's RwLocks, which we'll go into a bit more detail about later. This is the concurrent version of ref cell, and it blocks if it can't get a reference. So if it can't borrow it, it blocks, essentially means it sleeps. And then there's the mutex type, which is simpler than a RwLocks because it only allows exclusive borrows. So only one person can borrow it, whether it's mutable or immutable, whether you just need to read it, doesn't matter. You're the only person who gets access to it. And then atomics, which are like the concurrent version of a cell kind of thing. But those are platform dependent, and they only support certain types of T. So there's specific atomic primitives that the Rust language has, which we'll get into next chapter, in chapter 2, which is all about atomics. And the unsafe cell is the type that underpins all of those other types that we've just, well, most of the types that we've just mentioned there. It has a get method, which gives you access to the data's raw pointer, and then it can then use that to mutate the data because it's a raw pointer. It's using unsafe code, that's why it's called unsafe cell. And if you look at the implementation for cell, if you can just look at the source code for this, you can see that it's a struct that has an unsafe cell inside of it. And when you call get, it uses the unsafe for you, and the reference itself gets the value. It's safer than just using this type directly because it makes sure that cell isn't sync, and it does various other things to make sure that you won't get data races, which we haven't actually talked about yet. So let's talk about sync and send. So these are traits to handle multi-threaded behavior. They inform the compiler of the thread safety behavior of a given type. So if a type implements send, then it can be sent to another thread. If a type implements sync, then it can be shared with another thread. So if it can be shared with another thread, then a tref can be sent. Basically, you can send the reference, which means essentially you're sharing it. And these traits are auto-implemented unless you're dealing with a more complex type, usually with unsafe code. Then you're probably not going to have to implement these yourself. You'll get them for free. If you have to implement them, you are essentially saying that you will do the checking to make sure that this behavior is consistent, and you're not going to end up with weird data races or anything else that could cause undefined behavior. For that reason, raw pointers aren't sync or send, but in types that wrap a raw pointer, they will then make sure that the behavior is consistent through things like having rules about how many mutable borrows you can have, having checks on things like that, mean that they can then say, okay, I'm satisfied that this is send or this is sync. And the unsafe keyword is indicating that the compiler hasn't checked that, the developers checked it. And if a type's not send, then you can't move it into another thread. So, for example, we said that ref cell's not send, so this will throw an error. If you do want to opt out of the type for some reason, but you don't contain a type that would opt you out naturally, then you can add a phantom data type, which is 0 size, and it basically just allows you to basically treat this struct as if it has a cell in it, but you don't actually have to put one in it. And that's what the phantom data is doing there. And so because cell isn't sync, it then makes our outer struct X not be sync either, which we might need for some reason. Cool. Just realized there's tons of messages in the chat. Alex, is there anything there I need to scroll back and read through, or is everything good?
No, there's some good discussion going on, but it's I suppose at this point, if anyone wants to jump in with a question,
yeah,
I'd be trying to answer them.
Perfect. So. Thanks, Matt. Okay, well, I'll power on then so that we have time for free form chat at the end. So when we're talking about locking, we often talk about mutexes. This stands for mutual exclusion, essentially what we were saying earlier, single access. When you lock a mutex, it returns a mutex guard. That mutex guard is how you get access to the data which the mutex wraps. Then when the mutex guard is dropped, the mutex is unlocked, so someone else can lock it again. And that's why when we talk about mutexes, we talk about them wrapping the data. This is an example of what that might look like. So here we've created a mutex that wraps an I32. We spawn a thread, and then each one is going to increment it by 1, but it's going to do that in a 100 loop. And in this case, the guard is still being held for the entirety of this block, because the scope of this guard is this scope here. So we're actually only ever going to see, like any other threads would only ever see the mutex value jump in lots of 100. You're never going to see it when it's at like 33, because it would never be able to read the data, because this thread, while it's incrementing it, has an exclusive guard on it. And you can see at the end that it's incremented by 1,000. In the case where the mutex throws an exception, the mutex, sorry, in the case where an exception is thrown while a mutex lock is held, so while a mutex guard is still in scope, you'll get the mutex will become poisoned. So that's this unwrap here. So int inner is consuming the mutex and returning the underlying data. But if the mutex was poisoned, i.e. there was a panic while someone was holding the lock, then that's instead not going to return just the data. It's going to return a result which would have an error in it if there was a panic. So it's worth mentioning lifetime. So C++ friends will be well aware of the joys and perils of lifetime extension, and how you write your code will impact how long a mutex guard is held for. So with like an if loop like this here, you get lifetime extension, which means when you're doing this lock, the compiler doesn't necessarily know whether or not this item relies on you keeping around the result of this call. Now we know that it doesn't, because we're calling unwrap and then we're calling pop, at which point we've got the value out, we can throw away the guard. But the compiler doesn't know that, so it extends the lifetime of the mutex guard, so you are going to keep hold of the guard for the entirety of this if block, which is important to know because you really want to hold the guard for as little time as possible so that other threads can potentially access it as well. If we'd done it as a separate statement, then we wouldn't have gotten that lifetime extension. This is just a regular item. We already have gotten rid of the mutex guard, and now we can process the item as we wish, while another thread might access the data inside the mutex left. As well as mutexes, there's also a reader-writer lock, which is essentially a multi-threaded version of refcell. So similar to refcell, it can you can have multiple readers of the data at any one time, or you can have a single writer. When you call read, it returns a guard just like mutex, but it will return, if you've done read, it'll be a read guard. If you return write, it will be a write guard. And the usual reference rules apply. And just like refcell, actually, no, sorry, not like refcell, because refcell panics. The usual reference rules apply. So if you try and call write to get a write lock, but someone else has a read lock, then the thread's going to block until it can get the resource. And the implementation of read-write lock is operating system dependent. So most operating system implementations of this will block new readers when a writer is waiting. And that's because otherwise you would end up, if you had lots of readers of this data, you could have a writer sitting there waiting forever, because when one reader's done with it, oh, another reader had also come in before then. So your writer never gets access. But if you make it so that when your writer is waiting, no readers can get a lock either, then it means that you'll just have to wait for the existing readers to like clear out so that the writer can write, and then all your other readers can come and get access. So speaking of waiting, one of the ways that we can do waiting is parking. So if a thread is waiting on some other thread to make some known progress where like they can't do anything until this particular thing happens on another thread, then it might you could choose to get that thread to park itself and then let the other thread, which it's waiting on, unpark it when it's done. And the way you do that is you say, okay, to put my current thread to sleep, I'm going to call thread park so that this thread parks itself. And then some other thread that has a join handle for the thread which parked itself might wait on a condition. And then once it's gotten to a certain point in the code, it might say, oh, actually, if this thread's asleep, wake it up because it probably has something to do now. But it needs to have the join handle for it to be able to do that. And that way it unparks the other thread so that it wakes back up and it can carry on. And that's probably clearest to describe with an example. So again, this is straight out of the book. Brilliant book. In this case, we have a mutex locked queue, and we've got a consuming thread and a producing thread. So our consumer thread here loops and tries to pop items off of the queue and print them out until there's none left. And if there's none left, there's no point it keeping checking. So this lock here would be locking the data. So there's no point it keeping locking the data. If no one's added anything to it, it's just holding onto the lock and preventing someone else adding to it. So you don't really want to just keep locking it. So instead you park yourself, knowing that somewhere else in the code, in a different thread, the thing that's actually putting data into that queue is going to call unpark once it's added data. It calls unpark, that then wakes up the consumer thread. It then can go through and pop the items off of the queue and do whatever work it has to do. In this case, it's just printing. It's worth noting that parking doesn't guarantee that your thread will stay asleep. So you can get spurious wake ups where a thread will just wake up without unpark being called. So your code needs to account for that. And if you call unpark when the thread that it's calling unpark on is not parked, then it's going to bank that unpark for the next time park is called. And that means that the next park won't actually put the thread to sleep. So if your consumer thread was like was awake, it wasn't parked at that point, and then your producer thread was like, okay, please wake up, instead of just throwing away that notification, the next time that the consumer thread calls park on itself, it's going to not actually do the park. It's going to use the previous unpark notification to say, I shouldn't go to sleep, I'm going to stay awake. And as we've kind of mentioned, you need to know which thread to wake up, so it doesn't work super well for multiple consumers. There's a really nice description of why that behavior of keeping hold of an unpark, even if it's not needed at that moment, is necessary. So consuming thread, in our example, might lock the queue, then try to pop an item from the queue, but the queue's empty. So instead, it's going to unlock the queue, and then later on, it's going to call park and go to sleep to wait for more items. But if between it unlocking the queue and calling park to go to sleep, the producer thread adds a new item and unlocks the queue again, and then tries to call unpark, we still want that unpark notification to get in. We still want to wake up, because otherwise it could just stay asleep and it would never get to see this item that got added. So because the producer's acting, because there was a gap basically in our instructions, that means something could slip in there. So we still need to keep hold of the unpark notification in order to wake up the consumer. A better fit for something like that is condition variables. So these wait for something to happen to data that's being protected by a mutex. There are two basic operations. There's wait, which takes a mutex guard, and there's various versions of it with timeouts, and also notify one and notify all. So the wait operations atomically unlock the mutex and start waiting. And what that means is this gap here can never happen with a condition variable, because you can't, this gap. So you can't unlock the queue and not have called unpark. And not have called park. I also didn't realize there is an equivalent to this in C++, and it's been there since C++ 11. So stood condition variables is there. This is an example of what that looks like. You might name your condition to say, okay, this condition is not empty, and you generally associate one condition variable with one specific mutex. In this case, we have the same queue that we had earlier, but this time, rather than using park and unpark, we're using this condition variable. So we're still doing the same thing where we are having to lock the queue, but this time we've had to turn it into having two loops in order to still have access to the mutex guard. But it's the same principle. We pop items from the queue, and then if the queue is empty, we're going to unlock the mutex and wait, but we're doing that with a single operation using this condition variable. So we're saying, okay, I'm going to wait on this condition so that I then will, and I want to use this mutex guard. So what that does is it's going to drop the mutex guard so that our producing queue over here can actually access the queue again. When this adds data to it, it's saying, okay, the queue's not empty, so I'm going to call notify one, anything that's watching this condition variable is going to wake up and do whatever work it needs to do. So you could potentially have multiple other threads are waiting on this condition variable to do their own thing. But this producer doesn't need to know about those threads. All it needs to know is about the condition variable to say, okay, this condition is now met, therefore I'm going to notify it. And this is just notifying one, but you could also do a notify all if you had multiple ones waiting on it. So we now not only have a mutex containing the queue, but we also have the condition variable to communicate that condition. We notify the consumer through the notify one method. And yeah, just to re-emphasize, that unlocking, waiting, and relocking is all done by the wait method. That was a serious whistle-stop tour, so I'll do a quick summary, and then we can just open for chat about what people thought of the chapter, what people are thinking for like going forwards, and just general thoughts in chat. So summary of the threads. Multiple threads can run concurrently within the same program and can be spawned at any time. When the main thread ends, the program ends. Data races are undefined behavior, which is prevented by Rust's type system. Data that send can be sent to other threads. Data that sync can be shared. Regular threads might run as long as the program does, and thus can only borrow static data, such as statics and leaked allocations. Reference counting, atomic reference counted types can be used to share ownership to make sure data lives as long as at least one thread is still using it. Scope threads allow you to limit the lifetime of a thread to allow it to borrow non-static data, such as local variables. Ref-T, in the context of interior mutable types, we think of as a shared reference, and ref-mutable we can think of as an exclusive reference. Regular types don't allow mutation through shared references, therefore we usually call them immutable types. But when we're dealing with interior mutability, this terminology of shared reference and exclusive reference becomes more useful. Some types have interior mutability thanks to unsafe cell internally. They allow mutation through shared references. Cell and ref cell are the standard types for single-threaded interior mutability. Atomics, mutexes, and RwLocks are the multi-threaded equivalents. Cell and atomics allow replacing the values as a whole, while ref cell, mutex, and RwLock allow you to mutate the value directly by dynamically enforcing rules. So in the case of ref cell, it panics if you try and borrow too many times, if you try and mutably borrow too many times, and if you have a RwLock, it blocks until you can access it. Summarize parking. Thread parking is a convenient way to wait on some condition, but when a condition is about data collected by a mutex, conditional variables, convar, are more convenient and can be more efficient than thread parking. I just wanted to as well just appreciate all of the parts of this book. It's got a really great foreword, and I really enjoyed this bit. Many of the spirited discussions about Rust concurrency remind me of my parents' long ago complaints about the inconvenient safety features that were being added to power tools, such as saws and drills. Some of those safety features are now ubiquitous, but hammers, chisels, and chainsaws have not changed all that much. Which I think is a great quote, and it made me think of the fact that unsafe cell is just dealing with a raw pointer under the hood. Like, that hasn't changed, but we now wrap it in these safe types so that if you're writing regular code, you don't have to think about these things that are easy to bite yourself with. If any of that was completely nonsense, we have a Phyllis concurrency video online about an introduction to async and Rust smart pointers video. We did do an atomics talk last year, but I forgot to upload it, and I still haven't uploaded it, so I'll upload that when I upload this one. But yeah, now we can just open for chat and discussion. Also, that was a bit of a dump of information for the first chapter, so I hope it made some sense. If anyone wants me to go back to anything, let me know.
No, it was great. I'm glad that you call %t, ref-t, and ref-mut-t, because when I was practicing my talk, %t became quite tedious to say after the 10th time. So ref-t is preferable.
Yes, yeah. Too many syllables in ampersand.
Exactly.
And just to mention, so in 2 weeks, we've got a regular meetup talk on Rust-friendly websites and web apps. And then and it's going to be taking the next book club on the 17th of May, which will be doing, chapter 2, but we're still looking for people to take chapters 3, 4, 5, and onward ones. So yeah, please get in touch.